Okay, so I hope to be finishing all the stuff with events that the one section that I missed today would need to know to catch you up. Basically, we're going to talk a little bit more about conditional probability. We're going to talk about independence, and I'm going to go back and give you an example, show how you can use the idea of conditional probability in a slightly different form to work with tree diagrams. Okay. So, if you remember I'll just go back. This was the definition of conditional probability that we just finished in the previous video. Probability of E given F is the probability of the intersection of the two events divided by the probability of the conditioning event F. So an example, select a card at random. Let's say E was the event, select a jack. F is the event, select a jack, king, or king. Jack, queen, or king. In other words, select a face card. Okay. So the probability of E given F then is probability E intersect F. But if you select a jack and you select a jack, queen, and king, that's really the same thing as saying you selected a jack. So that's really just the probability of E. So 4 out of 52 over 12 out of 52, 4/12. So a 1/3 probability. But the probability of E, which we call the unconditional probability, that means that there's no conditioning event. Or if you want to think about it, the conditioning event is the whole sample space, if you want to think about it that way. The unconditional probability is just the 4 out of 52, 1/13. That is not the same as 13. We changed our probability. Okay. So what are we doing here? Well, one way to think of it is we're restricting the sample space to all the seniors, but the total probability still has to equal 1. So that's why we divide by probability of a senior. Is you have to do what's called normalizing the total probability. One of the axioms of probability was that the probability, the sum of all the probabilities of the outcomes had to be 1. Well, the seniors had probability 1/4. So if we want to make that 100%, we have to divide by 1/4 so that the probability of all seniors is 100%. So it's a conditional probability is a way of changing the sample space, restricting it to a smaller event. Okay, let's look at the definition of conditional probability. If you rearrange the terms a little bit, or rearrange the factors in the definition a little bit, you get something kind of interesting. We get something called the multiplication principle. So, if the probability of F is not 0, so let me bring the definition up here. In this definition, let's say probability F is not 0, multiply through by probability F then, which we can do because it's not 0. What we get then is probability E intersect F is probability F times probability E given F. That's the second one I have down here. If you interchange the role of E and F, you get that if the probability of E is non-zero, then the probability of E intersect F is probability E times probability F given E. So what's going on here? Well, this is really saying, say you want to know the probability that two events occur. What this is saying is that you can take the unconditional probability that the first event occurred and multiply it by the conditional probability that the second event occurred, given that you already know that the first event occurred. So, for instance, say you say you want the probability that it's raining and you took an umbrella to school. So that could be computed as the probability that it's raining multiplied by the probability that you take an umbrella to school given that it's raining. So under the assumption that it's raining. Okay, so that's one example. Now, maybe you don't always take the umbrella to school, but it's certainly going to be a different probability than the unconditional probability you take an umbrella just unconditionally. So the reason this is important is this is exactly what you can use in tree diagrams. We use tree diagrams to get the outcomes, to count the outcomes and to enumerate the outcomes, but now we can put probabilities with them, where the probabilities are going to go on these branches that go out. We're going to put the conditional probabilities, and this applies to multiple intersections. So if you take 3 or 4 events and intersect them together, you just keep taking the conditional probability that all the previous ones occur. So what that means is you can just follow along the branches that go out to that outcome, multiply all the probabilities together, and that gives you the probability of following that specific path out to that specific outcome. Let me show you an example to really, in fact, I think it's kind of out of order here. Okay, so this was an example we did in class. The experiment here, it's not written down here, but I'll say it. The experiment was to roll a die, a fair die, once. And then if you got a 1 or a 2, you were going to toss a fair coin once. If you got a 3 or 6, you tossed a fair coin twice. That was the experiment. Okay. Now you can't really analyze this experiment assuming equally likely outcomes. This was the tree diagram that we got. Pretend the probabilities aren't here. This is the tree diagram we got, and all we did was just get a list of 6 outcomes. But because it weren't just rolling a pair of dice, we weren't just tossing a coin, there was this mixture of the two, and somehow depended upon what you did at first. We couldn't just say, okay, these are all equally likely outcomes. Think back to the example about the outcomes where you get a sum of 2 or 3 or 4 all the way up to 12 on the sum of the pips on a dice. You can't just say there's 11 possibilities, so they all must have probability 1 out of 11. The probability that you get a sum of 2 is much less than the probability you get a sum of 8 or 6, say. So you can't always assume equally likely. So what do we do in that case? We can't assume they're equally likely. Well, if you look at the tree diagram, we're going to put the probabilities here. Probability here is 1/3, 2 out of 6, 2/3, 4 out of 6. And then, since it's a fair coin, all these remaining probabilities are going to be 1/2. Okay, and then to find the probabilities, say, of heads here, just get a single toss with heads. Follow the paths going out. So 1/3 times 1/2, that makes 1/6. So probability of heads is a 1/6. 1/3 times 1/2 probability of tails is also a 1/6. Notice here, this table here, what I'm doing is I'm giving you the probability function in tabular form. This is a function. I'm not giving it as a formula. The formula is not the only way to give a function. Formula is just a shorthand for the function. But if it's a small number of possible outcomes, I can just list it for you. Just say this is the probability of this and this and this. And that's what I'm doing here. The other 4 outcomes, interesting thing happens. Follow the path, say for heads, heads. Follow the path out. 2/3 times 1/2 times 1/2. What does that make? 2/3, 1/2, 1/2. That ends up being a 6 as well. Since all these are a half, all of those are going to be a 1/6. Wow. So what it turned out that all of these outcomes are equally likely after all. But there's an important difference. In the case of rolling the fair dice or tossing the fair coins a certain number of times, we were assuming at the beginning that those were equally likely. From the beginning, that was the approach, that we assigned equally likely outcomes equally likely outcomes, and so we had equal probabilities for all the outcomes in the sample space. But this is a little bit different. Here, we kind of discovered that they were equally likely. That's, if I change the numbers or change the situation a little bit here, it's not going to be equally likely in general. So it was by the tree diagram analysis that we discovered they were equally likely, rather than the assumption at the beginning that they were all equally likely. So we're going to use this tree diagram. The main reason I give the tree diagram, when we do something called a binomial distribution later, we're going to use a tree diagram. And it turns out in that case, these conditional probabilities are actually just going to be the same as the unconditional probabilities. And this is something I'll talk about more. I talked about it with the 1 o'clock class, but I'll repeat it again for both classes tomorrow on Friday, because it's an important idea. But if the unconditional probability is equal to the conditional probability, it's because the two events are said to be independent. Okay, so basically what that's saying is it doesn't matter what happened in the previous steps. I don't need to know what happened. The probability is always going to be the same at that step of the tree diagram. And a lot of times that happens to be the case with these tree diagrams, is that the steps end up being independent of the previous steps, and so it makes the analysis much easier. Here, it's not. There's conditional probabilities. So we actually do different things based on what you got. So we're going to use that when we do the binomial distribution. We'll have some tree diagrams to look at. Okay, it's one more thing. Okay, so here, yeah, I'm talking a little bit about independence. Let's see. Yeah, so I'll pick up that. I'll review the idea of independence tomorrow. That'll be like the last thing that we review. And I need to talk about contingency tables before we can do the worksheet. So we'll start off tomorrow in class of review independence, and I'll give a little brief discussion of contingency tables. We'll probably have the last 15 or 20 minutes, say, to start on the worksheet, and then you can look at that over the weekend, bring it back on Monday, and we'll finish up the 5th lab on Monday. Okay, so quick introduction to independence. Two events are said to be independent if the probability of the intersection is the product of their probabilities. Okay, so this seems kind of like a definition that came out of outer space. Well, what does this mean? So it's related to conditional probability. The way you want to think about it is this. Note, if the probability of E is non-zero, this is really equivalent to saying that the unconditional probability of F is equal to the conditional probability of F given E. So go back to the formulas, and I'll go over this in class. If you go back to the formulas, and you look at the formula for conditional probability, this equation here is exactly equivalent, because if you divide through by probability E, this is saying the conditional probability is equal to the unconditional probability. In other words, the knowledge of whether F has occurred, so the probability you would assign to F is not changed by whether E has occurred or not. That's the key point. Whether E occurred or not does not update the probability. It remains unchanged. And it goes the other way too. If probability F is not zero, you do not change your assessment of the probability of E based on whether F occurred or not. They're the same. No new information. So, example, select a card at random. Same to E and F that we had before, the hearts and the 7. The probability of 7 of hearts is 1 over 52. Probability of heart is 1/4. Probability of 7 is 1/13. Multiply those two together, 1/52. Now, notice, so that means these are independent. 1/4 times 1/13 is 1/52. That's not the same as disjoint or mutually exclusive. It's possible to get a heart and a 7. The intersection is not impossible. It's 1 over 52, which is not 0. So do not confuse independence with disjoint. Okay.